Okay, so we're going to get started with system design techniques. Last time we had looked at a bunch of system design principles. Whenever you're designing a complex system, what are the kind of trade-offs that we must make between different design aspects. So I will just quickly go over it. It will also act as a review till we reach the point where we left off last time. Okay. So we looked at system design, which was the art and science of integrating several resources into a harmonious, well-functioning system. And of course, there's technical knowledge involved in the functioning of each component, but also how do you fit these components together? What kind of design choices or trade-offs do you make? So certain things are quantifiable, certain things are not. So things like simplicity, modularity, elegance of code and so forth, these are not quantifiable, but they're all the same. Designers have to make these choices. So we looked at the design space being consisting of performance metrics and resource constraints. Performance metrics are the performance objectives that you want to achieve, and resource constraints are the limitations in terms of available resources that your system has to follow. So sometimes some metrics can be some attributes can be metrics in one instance and constraint in another. So for example, we looked at latency. For example, a stock trading transaction may have latency as a metric, means a goal that you want to achieve, having low latency. Whereas in some other situations like satellite communication, the latency may be a resource constraint because there's a minimum latency to communicate over satellite links. Right? So we looked at various metrics and resources, time, space, money, labor, bandwidth, social constraints, standards, scalability, and so forth. So I won't go over each of these again. Again, feel free to stop me anytime you have a question. All right. So balanced systems, we looked at how when we are trying to achieve a particular performance for a system, and in order to improve the performance, the system, we have to identify where is the bottleneck resource. And once we identify a bottleneck resource, then we can add more resources at the bottleneck resource to achieve a particular constraint, right? So a balanced system is something where there is no single bottleneck resource, right? So it's a perfectly balanced system, which means that you can achieve the performance that you have been targeting at the least possible cost, having no extra resources than necessary. We talked about this example of Henry Ford's Model T car, where they would go to junkyards and find out how which parts are still surviving in these junk cars, and then they'll go back to their factory and make those parts cheaper, so they would reduce the cost of the car. So and we were into discussing these different common design techniques last time, and I will just quickly go over these till we reach binding and indirection. So multiplexing was the idea of trading off space, time for space and money. So what this means is you have a shared resource, and the reason you're sharing a resource among multiple users, for example, is that you don't want to spend money giving each user. So for example, your professor right now is being multiplexed. With this one professor and there are 84 students. But the reason this is the case is that you're trading off time for money. Right? Of course, the university can hire one professor for each student, but that will be incredibly expensive. So you have to do it just one professor, and you have to share my time among all the students. So So that's an example of multiplexing. And likewise, when you go to a bank, there is a bank teller who, you know, whose time is shared among multiple users. And in that case, you know, users will be standing in a line and they have to wait. So there's an increased queuing latency versus, you know, and that way the bank saves money by hiring fewer tellers. So you can have a temporal or spatial multiplexing along the dimension of time, or along the dimension of time that's temporal, and along the dimension of space, which is spatial multiplexing. So, and we discussed a few examples. One of the things we discussed was statistical multiplexing, meaning that sometimes you overcommit the resources, knowing that you don't have enough resources if everybody shows up. For example, again, banks do statistical multiplexing. We all deposit our money with the bank, but the bank doesn't have like a box with your name on it that says this person's money. They basically pool all the money together and then lend it to all the other people. So at any point, they're betting on the fact that not everybody will come and ask for their money back, right? So, but if everybody comes and asks for the money back, banks are in trouble, right? So likewise, in airline industry, for example, they overbook the flights, and if everybody shows up for their flight, then some people have to be left behind. Right? Okay, so these are statistical multiplexing, but then most of the time these systems work just fine because not everybody shows up. So, and likewise in computer systems, operating systems can allocate a lot of memory, more memory than they have. That's the idea of virtual memory. They can promise more CPUs than they have. They can promise more IO resources than they have, and so forth. And with the bet that not all processors will need all the resources at all the times. So we talked about pipelining versus parallelism. Usually, to speed up computation, you can add more resources, you can add more CPUs, in which case you can execute n tasks in parallel, or you can break up a task into multiple stages and pipeline the various stages so that you can have multiple tasks going through the pipeline at any given time. So so in both cases, you can end up with a bottleneck resource, a bottleneck processor, or a bottleneck stage that can slow down all the other processing mechanisms. So again, here we have to apply our balancing principle to add more resources to the bottleneck to relieve and to improve the performance further. Okay, any questions so far? All right. So we talked about batching, which was trading off response time for throughput. The idea there was that you could take a bunch of jobs, wait to collect a bunch of tasks, and then you would feed these into a computing system, and the computing system would work on these jobs, say first come first serve order. So so this way the CPU is always busy doing some job, and the overall throughput of the system is higher, right? Efficiency of the system is higher if this system is always doing useful work and not spending time in overheads like context switching and preemption and cold start penalty. Then the efficiency of the system would be higher. So batching is very good for increasing the throughput or the efficiency of the system, but it is bad for response latency. What that means is that tasks may have to wait for a long time before they get serviced. But in order to reduce the response latency, we have to introduce the idea of preemption. If you have a process running and then some other interactive task becomes ready, then you may have to preempt the currently running, say, CPU intensive task, and then switch to an interactive task. And then when the interactive task is done, you switch back to the previous CPU intensive task. So that way you can reduce the response time for interactive tasks, but at the expense of adding more overhead doing the switching back and forth, right? So the efficiency is not high, but then you get lower response time. So, and we looked at some examples of interrupt coalescing in network adapters, character batching for remote login sessions, and so forth. Okay. We also looked at the notion of locality, which is commonly also called caching. So with the idea of caching, it's that if you're using if you need some information, if the information is available close by, say in the TLB or hardware L1 and L3 caches or in a file system cache, then you don't have to go further away to fetch that data, and it saves you time. So the way you identify this useful information that you have to keep nearby is by looking at the principle of locality. Temporal locality means that if I've used a piece of data once, then I might need it again and again. Right? Like for example, in a for loop, there may be a variable I, which is the say index, and you're going to access that index repeatedly and increment it. So if it was close by in a cache versus out there in the memory, then you can save time. Likewise, spatial locality means that if I've accessed a piece of data once, then I'm going to access the nearby pieces of data very soon. So, it's good to prefetch that data and keep it close. So for example, in file systems, if you access a block, so for example, in a file system cache, if you access a block I, then the file system would infer that you're going to access blocks I+1, I+2, and so forth very soon. So instead of waiting for you to request these blocks, what the file system may do is it may go and read these blocks from the disk into the file system cache. This is sometimes called read ahead. Right? So by the time your process goes ahead and requests for block I+1, I+1 may already be in the file system cache. So you will save time reading from the disk. Okay. So this is spatial locality, right? We are exploiting locality in the dimension of space. So these principles are used in various contexts. Caching is a really old technique, but it is also one of the most frequently used, one of the most useful techniques in computer science. So if any system or any piece of data exhibits locality, your software should be exploiting that locality to make things faster. Okay, any questions so far? All right. So the other thing we looked at was the idea of optimizing the common case. So what this means is that if you write a complex piece of code, there may be some pieces of code that are executed often and some other pieces of code that are not executed as often. They're executed rarely. So your goal as a system designer should be to optimize the most frequently used piece of code for the highest possible performance or efficiency. So there's something called the 80-20 rule, and it doesn't have to be 80-20. You can call it 90-10 or 99-1 or whatever you want to call it. But the idea is that 80% of the time is spent in 20% of the code. This is just a way of saying that most of the time in executing a software is spent in a small piece of the code. So, for example, in an operating system, maybe most of the time is spent in the CPU scheduling code, and then very little time is spent in accessing some device driver for a specialized I/O device, right? So if you consider this as an example, then you want to make sure that your CPU scheduling code is optimized for the highest performance, whereas the other piece of code, like infrequently used device drivers, as long as they work, it doesn't matter whether they are super fast or not. So when you design a complex system, you don't know ahead of time which piece of your code is going to be used heavily. So you would normally instrument your code. You will identify which parts of your code are by instrumenting the code, what we mean is that you insert measurement code inside your regular system to measure which parts of your code are being invoked. And then once you identify frequently used parts of code, then you can optimize those parts. So in our own research group, for example, what we do is we use a tool that's called PERF, P-E-R-F. And PERF is a very useful tool. And what it does is it inserts, it takes samples of your code as it's executing the instruction pointer, and then it maps them against the symbols, and then it can tell you which functions are being invoked and how long each function takes to execute and so forth. And then you can plot this entire output in something called a flame graph. So if you're out there, developing any piece of complex software, you might find that these tools are actually very useful in improving performance of your system. So you can just Google search for these and try it out. If you have a project going on, you can try these out. Okay. All right. Any questions? Comments? All right. So the other concept is the idea of hierarchy binding and indirection. So if so at the beginning of the class, and I've been repeating it throughout the class, any problem in computer science can be solved by one more layer of indirection, right? So that's where this concept ties in. So hierarchy has to do with scaling. For example, if you have a bunch of resources and you want a way to distribute, say, computation or distribute organized information, then the common technique is to use hierarchy. We've all learned about the tree data structure, for example, or various variants of tree data structures. We know about file systems. File systems are organized as trees. So what we're talking about is hierarchy, right? And if you look at how processes are organized, you have the root process, you have the init process, and then the child processes, and so forth. So they are again organized as a tree, right? As a hierarchy. So what hierarchy does is it distributes responsibilities down to lower granularities, so that there's not a central bottleneck, central place where that becomes a performance bottleneck. So hierarchy is also used in things like computer networks, where you may have large IP subnets. Like for example, the entire university has some core subnet, and then within that there may be smaller subnets, that sub networks that are handled by individual system administrators and so forth, all the way down to your computer, right? So again, there's a distribution of administrative responsibility throughout every level of hierarchy. So binding usually refers to the fact that you want to so the description here is kind of vague, mapping abstractions to specific. But what we are referring to in computer science is, for example, you might have a resource, and you might want to give it a name. Okay, so you can talk to the resource. So, for example, every machine has a IP address, right? So that's an example of a binding. Or every person has an email address, or in a physical world, each person has a name, right? So you're bound to your name, right? So and likewise, in virtual memory, how are physical pages accessed? They are accessed by specifying a virtual page number. So that's the idea behind binding. So you want to bind a name to a resource so that the resource can be addressed. For example, IO devices, character devices have names under /dev, right? /dev TDY1, for example, might refer to some terminal, text terminal on the system, right? So if you want to refer to that specific terminal, you refer to it by the name. It sounds kind of obvious, but it's really important to understand binding. If you can't name something, you can't access it. So naming something properly is naming a resource correctly and properly is really important, because once you can name it, you can associate permissions with the resource. For example, files have names, right? So it's kind of intuitive concept, but also very basic concept. So this whole idea of associating names with resources is called binding. Now, and a very closely related idea is that of indirection, meaning that if I want to access a resource, then I know its name, then how do I find it? Okay, so for example, let's see. Let's say that I know somebody's name, and in not so long ago, people used to have telephone directories, right? So if you knew somebody's name, you could flip through the telephone directory, find the name in the telephone directory, then you find out their telephone number. Okay, so this is an example of indirection, meaning that the telephone directory in this example provides you an indirection to figure out the telephone number from the name. Okay, and even before that, a long time ago, before there were telephone directories printed, people used to call up the operator, right? So you wouldn't even know the phone number. You would call up the operator and say, I want to talk to this person. You just give a name, and they will plug some wires in, and they will connect you to the correct person. Okay, so that was another form of indirection. So indirection basically means that you want to establish a binding translation, but in order to do that, you refer to some other well-known location, like a telephone directory or a telephone operator. Likewise, in the computer world, you have to, again, when you have binding, you need indirection to resolve name to resource mappings. So let's say you know the name of a machine. For example, remote.cs.binghamton.edu, right? And then you say SSH to remote.cs.binghamton.edu. How does the SSH command know which IP address to talk to? Well, so there is a mapping from machine name to IP address. This is maintained by a service called DNS, domain name service. All right? And it turns out domain name service is a hierarchical giant. It's almost like a telephone directory for IP addresses. So you send the name into the domain name service as a query, and then DNS service returns back the IP address to you somehow, right? Likewise, there is for our email communication, we maintain aliases for each email address. We may not remember each email address, but we know the name of the person, and we have a contact list somewhere. Wherever we type the name, then it automatically fills in the email address. That's another example of indirection. For virtual memory for operating systems, again, we have this a process accesses a virtual address from which a virtual page number can be extracted, and you can convert that to a physical page number by looking up a page table, right? So that's another example of indirection, right? Likewise, when you make a phone call, with your cell phone, if anyone still does that, everyone is on Zoom these days. So well, you don't even remember the phone number now. You just remember the name and the context. But let's say you get to the phone number, but phone number it has to be associated with a device, right? And we can change our cell phones, for example, and then we can keep our phone number. So there's a binding from the phone number to the actual device. So it could be, your and your cell phone could be anywhere. You might be driving, or you may be at home, or you may be at the office. So there's an indirection. When you dial a phone number, you have to find the device. You have to associate it, figure out what device it is and where it is, and then establish the connection. And just like DNS for IP addresses, mobile cell phone operators have an extensive infrastructure for doing this resolution. Okay. So the point of going through this is that this is hierarchy, binding, and indirection. We use these all the time in our day-to-day world. Just that now we have this idea that okay, these are relating to the same concept, right? And when a similar thing is required for another new system that you might develop, then you can apply similar principles based on what you have learned. Any questions on this? Okay. So we have spent quite some time on virtualization. Again, I won't spend a lot of time, but almost every resource, computer resource, can be virtualized. You can, for CPU, memory, I/O operators, I/O devices, including the entire machine, like the combination of CPU, memory, and I/O devices together to represent virtual machine. Likewise, networks can be virtualized. You have physical networks, physical wires connecting computers, but you can have virtual networks on top of it with a different virtual topology that may be different from the physical topology. Right? So pretty much, all the physical, all the networking that we are using these days is, in some sense, virtualized. So, and it's increasingly getting to be so. Virtual private networks where you can have encrypted tunnels to your, say, enterprise office environment, virtual overlay networks, web hosting infrastructure. There are different kinds of virtualization in different settings, but the key concepts are the same. And then there's an interesting example of names of call center representatives. What that means is that sometimes we call, say, customer service center, and then you start talking to some person and they say, hi, I'm John or Julia or whatever, right? And then the next time you call and then you say, I want to talk to this person. Well, that person may have left, but then a new person may have taken the place, but then they take the old name. So, so this is a way of virtualizing the call center representative's name. Again, another level of indirection. Right? Randomization it's not necessarily related to randomization. They're not virtualization. They're on the same slide. Randomization is a very interesting technique that shows up in many different scenarios, but it's usually used to break a tie, right? So normally in real world, it's like tossing a coin to solve something, right? To break a tie, so like who goes first in a game. So if the umpires will toss a coin and they call heads or tails, right? So and it turns out randomization is also a very good way of solving a tie, breaking a tie in computers. For example, CSMA-CD, carrier sense multiple access / collision detection. Okay, so you don't have to remember that, but this is used all the time. If you're using Wi-Fi networks, then you're using CSMA-CD mechanism, and this is running all the time to break a tie. What kind of tie? Well, your laptop may be talking over the wireless network at the same time as another person's laptop near you. And if they both talk at the same time, then just like with physical people, if two people are talking at the same time, there will be collision of their voice signals, and nobody will be able to understand what the other is saying. So how do you solve the problem? So like similarly for computers, two computers can't talk over Wi-Fi at the same time. So to solve the problem, you have to break a tie. So what do you do? So each of the computers would start talking, and if they sense that they're colliding, their signals are colliding, they would back off, right? But backing off means, let's say both computers say, all right, each of us are going to back off for 1 second, and we start talking again. So you're again going to collide. So if the algorithm for backing off to staying silent and retrying was deterministic, then you will keep colliding. But if instead you use randomization, that would be like, just like, with in the physical world, if two people start talking, normally they would back off, and then for a random amount of time, and one of them will try to talk again, right? Likewise for computers, they would back off for different amounts of time, and one of them will try to talk again. So basically each computer will throw a dice, and then whatever number they get, they use that as a wait time to talk. So it's a very interesting, very simple and powerful idea, and that is widely used. Routing is another example of randomization. And one of the interesting facts about internet routing is that, let's say you send a packet from here to the other end of the world, right? Most of the people, most of the ISPs along the way would use some form of randomization, which means that they're taking your packet and they're sending it out to somebody else, but then this packet doesn't belong to them. So they want to get it out of their network as quickly as possible. So you use something called hot potato routing. Hot potato means somebody throws you a hot potato. If you're going to hold it in your hand, it's going to burn you. So you're going to like throw it to the nearest person near you. It doesn't matter who it is, right? So most of these ISPs would use hot potato routing with their packets. They would randomly throw it to the nearest exit point from their network. And somehow the whole internet still works even with this hot potato routing. Of course, there's something called border gateway protocol, but then within that, this hot potato routing plays a major role. And that's again an example of randomization. And then I won't go into multicast NAC explosion problem, but that involves getting into the details of networking protocols. Okay. All right. Any questions so far? Okay. Soft state is another way of improving reliability. What that means is, so there are two terms, hard state versus soft state. So what that means is, if whenever a system stores information about the state of another system over that it may be dealing with, and then uses that stored state, then it's the hard state. Soft state is when you don't remember information beyond a specific transaction. So an example is TCP connections versus UDP connections in networking world. Like when you establish a TCP connection with another computer, then the two computers remember that we have a connection and how many bytes we have sent and which bytes have been acknowledged and so forth. And the state at the two ends lasts as long as the two computers are talking to each other, right? But then if one of the computers dies or the connection breaks for whatever reason, the other side tries to recover, and because it has the state information stored. So it makes the entire protocol more complicated, right? On the other hand, UDP, for example, is an example of soft state, which means that you don't actually remember the state about the other side. Instead, you just construct a UDP packet, put some address on it, and send it out. And the network figures out how to get the packet to the other side. But then, the sender doesn't remember anything about the receiver after that. And the receiver, likewise, when they get a packet, they process it, but then they don't try to keep the connection alive or anything like that. So soft state mechanisms have higher overhead because each transaction requires more information. Hard state mechanisms are more efficient because once you establish a TCP connection, for example, you don't have to repeatedly give the entire socket and port information well, you don't have to put them in the address, but then the sending application doesn't have to specify these for each and every message. Another example is, for example, storage is network file system. That's an example of using soft state, where you're accessing some files over the network from an NFS storage server, but the storage server doesn't remember you every time. So you have to make a fresh new request, whereas with specifying the file information and so forth every single time, and fetch these over the NFS protocol. So again, if the remote machine accessing the file dies, for example, the server doesn't remember anything about the client. So it doesn't have to do any recovery from the failure, right? And when the client comes up, it can just start off from wherever it left off, without having to reestablish the state back to where it was. So this is, so soft state is used extensively in many systems. And there are different, as a system designer, you have to think about whether you want to design a system with hard state or soft state. Any questions on this? Okay, so another example is, I just want to throw this out here, address resolution protocol, ARP, right? So this is another example of a soft state. So what you do is, whenever a machine wants to resolve IP address to MAC address or network device address mapping, use something called ARP. And ARP, this mapping information, whenever it is resolved, it is stored in a cache on each computer called ARP cache. So ARP cache is a soft state, meaning that the cache will store the mapping for some time, but if it is not used, then it's going to forget the mapping after some time, and then you'll have to reestablish the mapping all over again. So you can actually try it if you're on a Linux machine or any Unix machine. You can do ARP -A, for example, and it will print the ARP cache, which will give you all the IP address to MAC address mappings at a given time that your computer is remembering. And then you will see periodically it gets refreshed, it gets cleared up. Okay. So hysteresis is another interesting concept. So think about your thermostat at home, right? So let's say you set the temperature to let's say 72 degrees centigrade, all right? 72 Fahrenheit, not centigrade. So what would our expectation is that if the temperature falls below 72, then the heating will turn on, right? And if the temperature goes above 72, then the heating will turn off. Okay. Or if it's summertime, then the air conditioner turns off. It's above 72 and turns on. It turns on if it's above 72 and off if it's below 72. So, but if this was based on a single threshold, then think about what would happen. Your temperature goes from 72 to 72.1, right? And immediately your heating will turn off, right? And very soon your temperature may fall to 69.9, and then the heating will turn on, right? So you would have rapid oscillations back and forth around the value 72. And obviously we don't want that, okay? So because soon your furnace in the house will blow up. So instead, hysteresis says that you want two thresholds, right? So when we are setting a temperature of 72, we are really saying we're going to set two thresholds. Let's say, I'm just making this up. So they say 69 and okay. So yeah, you're right. I'm talking out of my head right now. So let me do this again. All right. Thank you. so if you have rapid oscillation, right? So you would have, so let's say 71.99 and 72.01. Okay. But then if I increase this threshold, if I had like two separate thresholds, I could do, 70 and 74. Okay. So what that means is that if my temperature falls below 70, then heating should turn on. And if the temperature goes above 74, then the heating turns off. Okay. So by having two thresholds instead of one, I avoid this rapid oscillation, right? So because once my heating turns on, it would stay on till I reach whatever, maybe 72, and then it turns off, and so forth. Okay, so you're not basically stressing. You are trying to avoid rapid oscillations around a single threshold value. So that's a physical world example, and you can also apply this to computer systems. For example, in paging, memory paging system. So whenever memory gets full, then, or it's about to be full, then we want to swap pages out, and, and then we want to bring pages in when they're needed, right? But then, you could, for example, let's say we said we had like 90% memory usage was our threshold for swapping pages out. So you'd say if our memory usage is 90%, we start paging, we start sending pages to the disk, and so if it is memory usage is more than that, then we page out pages to the disk, to the swap device, and then once it falls below 90, then we stop sending pages to the disk. So again, the same threshold issue will happen, when we reach 90.01% memory usage, then the swapping will kick in. But then as soon as it reaches 89.99, then swapping will stop, right? But what will happen? Somebody is going to do a malloc right away, and the memory usage is going to shoot above 90% again, and swapping mechanism will still kick in again, right? So again, you will see rapid oscillation in the performance, because whenever you're swapping things out, it slows down other activity. So instead, you might have two threshold values. So instead of having one threshold value, I might say, if my target is 90, I might do say 85 and 95 or something like that. So having two threshold value gives me more room for avoiding rapid oscillations, right? So what that means is if my usage goes about 95%, then I keep swapping, paging things out till my memory usage falls to 85%, right? Then it will take some time for the usage to get back to 95 before I start swapping out again. So it gives me some buffer to maintain a stable state in the system. Okay. Does it make sense? Any questions? Okay. So another idea is to separate data and control. So what that means is that, again, this comes with, making the common case process related to this idea. Take the example of routers. Routers are these devices that are connected to multiple networks, and then you get packet from one of the networks. The routers have to send it out on another network, right? So the most of the time they are forwarding data packets, and they have to do it at a very fast rate. And this has to be usually implemented in the hardware. But then there's another component which controls the functions of the router, the configuration of the router. And the control aspect is the which is also important, but control is infrequently invoked, right? So it can be implemented separately, and usually control aspects are related to policy. For example, a system administrator may have to change the configuration depending on various parameters. So control and data can be kept separate. The policy can keep changing from time to time, whereas the normal operation of forwarding data packets have to be done all the time, right? So usually data forwarding is implemented in hardware, and control operations are implemented in software. And there is a way for interface between the control software and the hardware. So, and likewise, for operating systems, like for example, page replacement that we just talked about, the mechanism of swapping can be implemented inside the OS, because OS is responsible for writing pages out to the swap device. But the policy for swapping, whether the threshold is 85 and 95 or 80 and 90, that policy aspect can be changed. So there's a control aspect. So there's a control plane and a data plane, right? Or there's policy versus implementation, and these are usually separated. Whenever you design a system, it's always a good idea to separate policy and implementation, or data and control. Right? So, and there's additional example for for networking, where there's virtual circuit establishment, which has similar concepts. So, and a different concept is that of extensibility, in that whenever you're designing a complex system, you have to keep in mind that the system may be extended in the future, right? In ways that you cannot potentially anticipate. So it's always a good idea to leave some mechanisms for extensibility. For example, right now the world is transitioning, or has almost transitioned from oops, what did I just do? Okay, I am not sure what I did with my okay, so let me try to get it back. Sorry about that. Share. Okay, so let me try one more time. Yeah, with extensibility, for example, the world is transitioning right now from IP version 4 to IP version 6, where we're soon going to run out of IP addresses to give to all our devices that are proliferating, right? From our cell phones to Internet of Things. So IPv6 is supposed to help us with that proliferation. But then when people designed IP version 4, they didn't know what IPv6 would look like. They didn't even know what it would be called. So they left like a tiny field in each packet header that would specify the version of the packet, right? So they knew that in the future, if these protocols will be redesigned, they would need, by looking at the version number, you can know how to interpret the rest of the packet header. So that was an example of allowing a hook for future extensibility or future growth. If they had not left that space, a tiny field at the beginning of the IP header packet, then it would have been impossible to transition to a new protocol, because all the routers that it would have been designed without looking at that header field, right? So just like a small design decision actually has such a huge impact down the line, right? And it requires you to be thinking ahead that the system I'm designing may not be the system that will be used in the future. So I have to provide a transition path ahead of time. Okay. And likewise, the same idea is applied for HTTP. HTTP is the protocol on which the entire web is based, but then there are various versions of HTTP protocol, and browsers have to interpret the various versions of HTTP protocol. So there's again, version field in the corresponding HTTP documents. So This is used in modems. For example, two modems are talking to each other. One of them may be an old modem, one of them may be a new modem. How do they know what data rate to talk to? So again, there's like a data rate that's exchanges in the beginning based on which modems synchronize with each other, and so forth. Kernel modules, you have all run into this problem. Kernel modules have a version field, right? So that you know, if there is like a mismatch with the kernel version into which you're inserting the module, then this can be detected ahead of time. Okay, so this is again something you have to think of it as a designer, not just that the system should work, but how will it scale and evolve. Okay. So we've gone through a kind of a big, you know, assortment of techniques. Some of them are very high level, you know, but hopefully with all the examples, you can start to get some sense of where these may be important, how different ideas in different fields actually are related to each other. They're expressing the same concept, right? So again, you know, if you find a good idea, you just put it away, and then you can reuse it again and again in different contexts. So, so these are like tools in our toolbox, and we apply whatever tool is necessary for a given job. Okay, so I think that is the last slide of the entire semester. Any questions? Comments? All right, so I'm going to do a quick review. Before I do that, I want to just remind everybody to complete their suit scores, suit survey. If you go to suit.binghamton.edu, so there, you know, you can fill it in. It's very fairly easy to do this, and you know, you don't have to, you know, very quick feedback. It shouldn't take up much time. I know everybody's busy, so please do that. The deadline for doing this is tomorrow, May 5th. Okay. So let me get back. What I want to do now is kind of do a quick review of the materials. Okay, so I'm going to go all the way back, and I'll try not to cover each slide, but the general rule of thumb is, you know, to of course review the slides and the references for each chapter, and then, you know, also try to go over the sample questions to see what concepts are important. So with, you know, system calls, for example, you know, we have learned how system calls work, but understanding why there is a special mechanism called system calls. How are they different from function calls? What is the privileged transition operation in system calls, right? And what happens in the execution path of a system call? When you make a system call, what happens to the process state? What if the process has to block for some event? Then how is that handled? So relating these together, right? So system calls are one of the mechanisms by which OS code is invoked, right? There are also other mechanisms like traps and you know, exceptions and hardware interrupts and so forth. So yeah, how do system calls work? What is a system call table? You know, for every system call, there's a system call number. So the OS has to look up where is the corresponding implementation for system call. This is something called a system call table. And then how is the CPU privilege affected when you make system calls. You transition from user space into supervisor or OS mode and then back. So you need to perform a safe transition between these two modes. Right? So what else? So we just talked about this in the earlier class on segmentation as well as maybe earlier in the course. Some OS operating systems would map themselves into the address space of each process, is to make the system calls faster, so that you don't have to do a context switch. But there's also a security implication of that. Certain side channel attacks can exploit this mapping mechanism to compromise the kernel. And so as a result, there's an alternative where you can have the OS running in a separate address space. And then when you make a system call becomes an operation, remote, basically communication from one process to another address space, right? So system calls become more expensive. So yeah, I won't go through each and every question, but yeah, feel free to review these and ask me if you have other questions. Any questions about system calls so far? Okay, so there's a question of all the chapters. Can you specify which one we should focus on more? Well, I don't want to like. I'm going to give, my idea is to give questions from each of these chapters. Okay, at least one question from each of the topics. All right. But if anything, focus on the key concepts in different chapters. And if you are limited in time, then I would say, focus on the topics that are, highlighted in the sample questions, for example. So, and of course, I'm aware that we have given a written assignment which covered part of this. So I'll try to balance it out for the topics that were not covered. So if you have to prioritize, then, start going backwards and cover the later chapters first. So that if you run out of time, then, you have already studied the other chapters for your earlier assignment, right? But virtual memory is important. I would urge you not to skip it. Okay, there are at least be a couple of questions on virtual memory. Okay, so okay, and following my own advice, I would go backwards. Although, let me go from top to bottom because those are the topics we haven't covered for a while. Right. So we spent a lot of time on TLB coverage and super pages, and this is again, important to understand. What's so important about TLB, translation look aside buffer. Why is it really important for performance perspective? What's TLB coverage? What happens if there's no TLB? Why do we have different super page sizes? Why not just one page size? What impact does it have on the TLB miss ratio? All these things. Okay. So, in respect to the super page paper, we covered these concepts of preemptible preservation, incremental promotion, speculated demotion. So how do these three key concepts work, right? And the idea of internal and external fragmentation, how do both of them become worse? And why do they become worse? Okay. So, and why is contiguity, again, related to the fragmentation problem, why is the contiguity restoration important? Okay. Let me go back. So segmentation we just covered, so I'm not going to go over that How is it related to virtual memory subsystem? What's the benefit of segmentation versus paging? How are each of them? In what context are each of them useful? How does, if you had segmentation, how does virtual to physical address translation change compared to what we learned with just pure paging? If you had segmentation, how does that translation mechanism change? Okay. So for the Unix time sharing system, we discussed this in the context of file system. And again, the excuse there was to study file systems. And what is a file system? Why is it not enough to have just data? Why do we need metadata? And how is metadata stored and managed? So in this case, this would be inodes. So there were various mechanisms that build up to inode. But the key concept here is the inode. How does inode work? How does it provide a logical block number to physical block number mapping? Just like page tables map virtual page number to physical page number, likewise inode should map virtual block number to physical block number. Right? So yeah, we talked about what kind of I/O operations go down to the disk. Like if you do look at the I/O operations at the disk level versus above the file system cache, you would see that below the file system cache, right above the disk, you would see more write operations than reads. So what kind of a role does file system cache play in doing this? So most of the reads get filtered out by the cache, whereas writes make it through the cache, and thus they would end up going down to the disk more. So as a result, disks are often optimized for write operations for improving write I/O throughput. Okay. So we also talked about log structured file system. Talked about the role of file system cache in both speeding up read operations by exploiting locality, and also buffering the write operations. Means that you could write into the file system cache and return back to the user application, and the writes can be committed later to the disk. So you can go over, there are some of these things we haven't covered here. These are usually something I covered in undergraduate class. For example, path name conversion from the path name to an inode. But it's interesting. I would urge you to think about this. This might be there in my file system video lecture, but it's an interesting concept. I don't think I've covered it in the class. Okay, so there are numerical questions here related to inodes, and again, these are some of these you got in your earlier assignment. So you might want to just refresh some of these again, based on what you wrote in the assignment. And I'm not going to go over each of these, but all of them are variations of the same idea. You're given different parameters of the inode, and you're asked to compute something or the other with respect to the file size or the inode size and so forth. Okay. All right, any questions on this? Okay. So we again spent quite a bit of time on RAID, and we talked about how RAID extend the virtualization concept to storage devices. Basically, we're doing a many-to-one virtualization. We take many disks and then we map them to
Professor, I think we lost sound.
Sorry. So somebody has their mic. Okay. I'm not sure what's happening. All right. Can you hear me now? Okay, good. I don't know. Suddenly everything started blowing up. I think it's a sign that I should stop talking. It's the end of the semester. Let everyone go. Okay, so yeah, so just what I was saying was for rate, we covered various rate levels, parallelism, throughput comparison, and so forth. Right? You did some of these in the earlier assignments, so just review those concepts again, and look at these sample questions. How are different level parallelism, and how is the parity information computed? How is the parity information distributed, and all those things? Okay. Any questions on this? All right. So IO models is, again, the key thing is to understand the difference between different IO models, and to know in what context you would use, with blocking IO versus non-blocking IO, signal-driven IO, and so forth. So why are each of these levels useful? Where would you use them? And how do they differ from each other in terms of how they treat two stages of IO operation, right? So receiving data from the IO device and copying them to user space. So which stages do each of these block, and how do they work? Okay. So virtualization, we again covered a lot of ground there. We looked at a classification of virtual machines, process VMs, system VMs. And then within system VMs, we looked at individual resource virtualization, CPU, memory, and IO operations, right? So IO device virtualization. We looked at hardware support for virtual machines, system virtual machines in particular. We looked at type 1, type 2, classical VMs, hosted VMs, para-virtualized VMs, and so on. So again, important to understand what each of these mean and how they differ from each other. So you don't have, I wouldn't say memorize any of these, because it's open book, right? You can also refer to it, but it's important to understand the concept so that you can interpret the question properly and answer what's being asked, right? Rather than just reproducing what you have memorized. So live migration, again, we looked at different live migration techniques, stop and copy, demand paging, post copy, pre copy, and hybrid mechanism, plus a few more like scatter gather migration and gang migration. So, so understanding how pre copy, post copy work, and how we can build upon these for other techniques. Why are these necessary? What is liveness versus non-live migration? So these are some of the things you want to focus on. Okay. Any questions? All right. So we also looked at containers, and this was an example of operating system level virtualization. We looked at how containers differ from system VMs versus processes, the relationship to chroot jails, and how containers themselves consist of namespaces and and control groups, right? So, yeah, and to understand this idea, and the key idea that the containers share an operating system underneath, and they're only isolated in the sense that one container cannot name the resources belonging to another container. So that's where the idea of namespaces comes in. So their virtual isolation model is not as tight as system virtual machines, but they still provide sufficient isolation and better performance than system VMs, right? Because they're sharing a common operating system. So understanding the key differences from other techniques and what kind of virtualization these provide. Okay. So, and I won't go over system security and principles. In system security, I just want to focus mostly on, I know I covered a lot of topics in system security, but you want to focus more on OS concepts, OS related concepts, which is, things like, what are the CPU memory and IO level mechanisms for that are involved in enforcing security and access control. What are the role of privilege levels, for example? x86 ISA has 4 privilege levels. And yeah, these sample questions are a good guide to what to focus upon. Right? So of course we talked a lot about authentication, viruses, worms, insider attacks. That was just to give a big high-level overview, but focus on the OS level mechanisms for security that are represented through these sample questions. Of course, access control is an important OS function too, and in particular, we looked at mandatory access control or multi-level security. So that that's also important. No read up, no write down principles, and the idea of a trusted computing base, TCB. What is a trusted computing base? What does trust mean? And what's a reference monitor? Why are these important? Okay. All right. And the lecture that we just did today, the key concepts, the trade-offs involved, and what's the idea of a metric versus a resource, performance metric and resource constraints. So, any questions? I know this is a very quick review, but I'm sure you will have questions, but it's a good time to ask. Okay. So that's